What is a qubit? A qubit is the quantum version of a classical bit, which in classical computers is either a 0 or a 1. In contrast, a qubit can exist in multiple states simultaneously thanks to quantum mechanics. A qubit is typically represented as a vector in a two-dimensional space, often a sphere known as the Bloch sphere, where 0, pronounced ket 0, is the state corresponding to 0. 1, pronounced ket 1, is the state corresponding to 1. However, a qubit can also exist in any linear combination, superposition, of ket 0 and ket 1, like this, where alpha and beta are complex numbers that determine the amplitude of the states ket 0 and ket 1, respectively. The amplitudes, alpha and beta, determine the probability of measuring the qubit in either the ket 0 or ket 1 state. Specifically, the probability of measuring the state ket 0 is alpha divides 2 alpha caret 2, and the probability of measuring the state ket 1 is beta divides 2 beta caret 2. The sum of these probabilities must always equal 1. Superposition. One of the most important features of a qubit is superposition, which means a qubit can represent both 0 and 1 at the same time, until measured. Example, a qubit in the state, this state is a superposition of ket 0 and ket 1. If you measure the qubit, you have a 50% chance of observing it as ket 0 and a 50% chance of observing it as ket 1. The actual outcome is random, but the system can exist in both states simultaneously while it's not being measured. In practice, superposition is one of the main reasons quantum computers can perform certain types of calculations much faster than classical computers. This is because, with superposition, quantum computers can explore multiple solutions simultaneously. Entanglement. Another powerful property of qubits is entanglement. When qubits become entangled, the state of one qubit becomes linked to the state of another qubit, no matter how far apart they are. This means that the measurement of one qubit will immediately affect the state of the other, even if they are on opposite sides of a universe. Entanglement creates correlations between qubits that allow for faster processing of certain computations. A system of entangled qubits can be used to represent and process information in a highly complex way. Example, if two qubits are entangled, and one is measured, the state of the other qubit is instantly determined, even if the second qubit is far away. For example, if you have an entangled pair of qubits in the state, this is called a Bell state. If you measure one of the qubits and it collapses to 0, you immediately know that the other qubit must be in state 0, and vice versa. Entanglement is what allows quantum computers to perform parallel computations at an exponentially larger scale compared to classical systems. Quantum interference refers to the way that the different probability amplitudes, like the coefficients alpha and beta, can interact with each other when qubits are manipulated. Interference can amplify or diminish certain outcomes. By carefully controlling the interference of quantum states, quantum algorithms can make the right answer more likely to occur when the qubits are measured. This allows quantum computers to use the power of superposition and entanglement effectively, guiding the system to the correct result. Qubit representation, the Bloch sphere. To visualize qubits, a useful tool is the Bloch sphere, a geometric representation of the state of a single qubit. The Bloch sphere is a unit sphere, where any point on the surface of the sphere represents a possible state of the qubit. The poles of the Bloch sphere spawn to the computational basis states. The north pole represents the state ket 0, and the south pole represents ket 1. A general state of the qubit can be represented as a point on the sphere, where the latitude corresponds to the relative phase between the Ket0 and Ket1 states. The longitude corresponds to the amplitudes of the Ket0 and Ket1 states. This visualization helps us understand how qubits can be manipulated using quantum gates. Quantum gates, operations on qubits. In quantum computing, operations on qubits are performed using quantum gates. These gates are analogous to classical logic gates but work in a way that takes into account quantum phenomena like superposition and entanglement. Some commonly used quantum gates are Hadamard gate. H places a qubit into an equal superposition state, for example, Ket0, Ket0 plus Ket1, /2. Poly-X gate. X flips a qubit, Ket0 Ket1, Ket1 Ket0, analogous to a classical NOT gate. CNOT, controlled NOT, gate, a 2-qubit gate that flips the second qubit, the target, only if the first qubit, the control, is in the state Ket1. Phase gate, introduces a phase shift to the qubit. Each of these gates is represented by a matrix and acts on the qubit states by rotating them in the Bloch sphere. Qubit physical implementations. Qubits can be implemented physically in different ways, each with its own advantages and challenges. Some of the most common methods include superconducting qubits. These use superconducting circuits and are the basis for many quantum computers being developed by companies like IBM and Google. Trapped ions. In this approach, individual ions are trapped using electromagnetic fields and manipulated with lasers. Photons. Qubits can be represented by the properties of photons, such as polarization or phase, which are controlled using optics. Topological qubits. A theoretical approach to qubits based on exotic particles called anyons, which are expected to be more stable and less prone to errors. Challenges of qubits. Decoherence. Qubits are extremely sensitive to external noise, such as temperature fluctuations or electromagnetic radiation. When a qubit interacts with its environment, it loses its quantum properties, a phenomenon known as decoherence. Error rates. Because qubits are delicate, the operations on them tend to have relatively high error rates compared to classical bits. Error correction techniques are a significant area of research in quantum computing. Conclusion. Qubits are the fundamental units of quantum information, exploiting the strange and powerful principles of quantum mechanics, such as superposition, entanglement, and interference. These properties give quantum computers their potential to solve complex problems much faster than classical computers. However, working with qubits presents unique challenges that researchers are still trying to overcome, such as decoherence and error correction.